Today we will be looking at sampling proportions. The distribution we get if we could see all proportions, all of the proportions from the possible samples is called a sampling distribution of the proportions. We would expect the histogram of the sample proportions to center at the true proportion P in the population. It turns out that the histogram is unimodal, symmetric, and centered at P. Remember our example of different sample sizes when we did the dice activity? Tomorrow we will be doing a number line, a table of random digits activity with some dot plots again. Okay, so very, very important. So the true proportion, if we were to take a histogram of that sample, the larger the sample, remember, the more normal our model appears and becomes. A sampling distribution model for how a sample proportion varies from sample to sample allows us to quantify that variation and how likely it is we'd observe a sample proportion in any particular interval. To use a normal model, we need to specify its mean and standard deviation. We'll put the mu, the mean of the normal, at P. Okay, so if we look at this table down below, the table tells us for a sample mean, we use an X bar. Okay, so sample, it estimates the mu, the true population mean. And remember, today we are talking about sample proportions. So P hat is the sample proportion, and it estimates P, the population proportion. And S, the standard deviation of the sample, estimates sigma, the population standard deviation. Okay, so today we'll be talking about P hat and P. Tomorrow we'll be talking about X bar and mu. Okay. When working with proportions, knowing the mean automatically gives us a standard deviation as well. The distribution of the sample proportions is modeled with a probability that is. Notice this is our mean here. So this is our mean of P. And then this is our standard deviation of P. So we find the sample, the mean, as the population proportion, and the standard deviation, we do the square root of the probability of success times the probability of failure divided by the sample size. Okay, so initially P hat, all it is the distribution of all possible sample proportions of successes in the sample size and draws from the population. And the hat over the P is important because it denotes sample proportion. So here's a picture of how our model would follow. So remember back in the day, last semester, this was our mean. Remember, this was 1 sigma, 2 sigma, 3 sigma, and then negative sigma, negative 2 sigma, and negative 3 sigma, meaning we're 3 standard deviations below the mean or 3 standard deviations above the mean. Everything is the same except for how we find the mean and standard deviation. We still find a z-score, we still use the chart or normal CDF in our calculators. Sampling error is not really an error at all. It is just the variability you would expect to see from one sample to another. Sometimes we see this as sampling variability. As we move through second semester, we will have specific conditions we will need to check and verify when we do our plan steps, when we get into inference. For proportions, there are 3 conditions. The first one being the randomization. The sample should be of a simple random sample of the population, or it should be representative of the population at whole. The 10% condition The sample size n must be no larger than 10% of the population. Remember last semester when we talked about bins for binomial distribution models, and we said if we are selecting a sample without replacement, then the sample needs to be less than 10% of the population. That is where the 10% condition comes in. And then we have the success failure condition or large enough condition. The sample size has to be large enough so that both NP and n times 1 minus p, or NQ, are at least 10. So these are the 3 critical things I will be looking for when you take your sampling distributions, formative and summative. Sampling distribution models are important because they act as a bridge from real world of data to the imaginary world of the statistic. Okay, so now we're taking real life data and applying some stats. They enable us to say something about the population when all we have is data from the real world. In our first example, the CDC reports that 22% of 18-year-old women in the U.S. have a BMI of 25 or higher, a value considered by the National Heart and Lung and Blood Institute to be associated with an increased health risk. As part of a routine health check at a large college, the physical education department usually requires students to come in and be measured and weighed. This year, the department decided to try out a self-report system. It asked 200 randomly selected female students to report their heights and weights. Only 31 of these students had BMIs greater than 25. Is this proportion of high BMI students unusually small? Just like we did last semester, the first thing we're going to do for any problem is start underlining key clues. We have this 22% of 18-year-old women, and then we have 25 or higher, which is not really that relevant. Note that we also have 200 randomly selected female students, and 31 of these students had a BMI greater than 25. Is this proportion of high BMI students unusually small? So for the second semester, all of our answers to questions will primarily fall into 4 steps. Okay, so essentially what we're going to end up doing is, it seems lengthy now, but it will be okay later. The first step is to do our state step. In this case, our state step, we start identifying what our population parameter really is. So we're going to say P is the true proportion of females with a BMI of at least 25. The next step is to do our plan. This is where we do all of our conditions. For our plan step, note that we have to do random. So 200 females were randomly selected, and remember we get that from our context. Typically, I will word for word look at the context and then write that down on my statement for the AP exam. If you do not, they may dock you from E to P. It is possible. The second one is the 10%, meaning 200 students or 218-year-old lady students is less than 10% of all 18-year-old females at a large college. Okay, if we're assuming a large college, I would assume a D1 school, which has a lot of students. And then last but not least, that success-fail condition where you have to show both successes and failures are at least 10, just like we did with binomial models. And because they both are at least 10, we can use a normal model. So step 3 is our do statement. This is where we're going to do all of our math. So for our do statement, the first thing that we are going to do is we're going to identify what our sample proportion is. So we would write P hat equals 31 over 200. And we get that 31 because up in the context, note that it says only 31 of these students had BMIs greater than 25. Okay. To find our standard deviation, we are going to take the proportion of success times the proportion of failure divided by the sample size. We know the sample size is 200 because it is given to us in the story. And we just type it all into a calculator and we get approximately 0.0293. Remember, the sample or the mean is going to be the same thing as the population proportion, which in this case is 22%, because it says 22% of women in the US. Okay, so that's the first thing. Then everything else is the same as it was last semester when we talked about normal models. So note, we're going to find a z-score, so 0.155, which is our sample proportion minus the population proportion divided by the standard deviation we found from our sample. We do get a z-score of negative 2.22. And remember, we can use normal CDF. Remember, you have to label the lower, the upper, the mean, and the standard deviation. Okay. It's also beneficial to draw a picture, because remember, to receive an essentially correct, you have to show that you're using the z-score formula. You have to show some sort of direction. And if you use calculator speak instead of the chart, you have to have everything labeled. In this case, when we do normal CDF, we do get an approximate proportion of 0.0124. That's our do step. The last thing to do is our conclude. Okay, so for our conclusion, according to the model, about 1.24% of women from the college have a BMI greater than 25, which is unusual. There could be errors in recording heights and weights. And then that's all we have in our problem. So look at the 4 steps we did. The first thing we did was we did the state step, where we state the parameter for the population we're trying to estimate. The second thing we did was our plan step. This is where we list our conditions and check to make sure they are verified. The third thing we did was our do step, in which we found the sample proportion, the mean, and the standard deviation, found a z-score, drew a picture, used our chart or normal CDF in our calculator. The last thing we did was take the information from step 3 and write a conclusion in context based on the question in the original problem. Guess what? We get to try another one. Woohoo! This time, we are going to suppose that about 13% of the population is left-handed. A 200-seat school auditorium has been built with 15 left seats, meaning seats that have built-in desk on the left rather than the right arm of the chair. For right-handed readers among you, have you ever tried to take notes in a chair with the desk on the left side? In a class of 90 students, what is the probability that there will not be enough seats for the left-handed students? Now, the desks they're talking about are those old school ones that flip up and over one arm of the chair. Typically, you'll see them in auditoriums and universities. Sometimes you will see them in classrooms, but I don't think I've seen them here at East. Remember, our first step is to do the state step. In this case, we're going to say P is the true proportion of left-handed people. Next, we will do our plan step. Okay, so remember, in our plan step, we're going to do our 3 checks. The first is to verify that we have a random sample. So in this case, we don't have a random sample, like we don't have enough information. So in this case, we're going to say assume the sample is representative of the population, or assume the students in the class are randomly assigned. Remember, the second condition is the 10% condition. If we are randomly selecting 90 students, 90 students should be less than 10% of all students at that school. And then success failure condition, remember you have to do your sample times your population proportion, which in this case is 13%, and we get that because it says 13% of the population is left-handed in the first sentence, which ends up being about 11.7. And then you have your sample size with the failure rate to be about 78.3. And since both NP and NQ are at least 10, we can use a normal model. Okay, now we're ready to do our do statement. So remember, for our third step, the do step, the first thing we will do is we'll figure out what our population proportion was. So because we know we have 15 left seats, okay, and we know we have 90 students, our population proportion is going to be about 0.167. Remember, your sample mean is going to be the same as the population proportion, 0.13. And your standard deviation is the square root of n times 1 np. Oh, no, I'm sorry, excuse me. The standard deviation is the square root of the probability of success times the probability of failure divided by your sample size. So we'll do the square root of 0.13 times 0.87 divided by 90, and then square root it. We do get about approximately 0.354. Next thing we'll do is we'll find a z-score just like we did last semester. And when we plug in the appropriate items into our z-score, we do get about 1.05. Remember, it's a good idea to draw a picture. Remember, you want to have your population proportion labeled. You want to have the normal model statement up at the top. You want to have where your sample proportion would fall. And you would want to have a number that represents the shaded region with the appropriate shading. And remember, the reason why we shade to the right, because the question says, what is the probability that there will not be enough seats for the left-handed students? So that means we have more than 15 lefties in this class. All we have, remember, you can do a normal CDF statement as well, but make sure you label the lower the upper the mu in the standard deviation. All we have left to do now is the conclude statement. In our conclude statement, we're going to say, according to the model, there's about a 14.46% chance that there will not be enough seats for the lefty students in this class. So remember our critical 4 steps that we did to do this problem. The first thing we did was we did our state step, where we stated what the true proportion, whatever it is we're trying to estimate in context. The second thing we did was our plan step, where we had 3 specific checks: random, 10%, success, fail. The third step is the do step. This is where we find our sample proportion, we find our mean, and we find our standard deviation. We also find our z-score from that step, use the chart or normal CDF to get the proportion, or the probability of this actually happening. And then the fourth step is the conclude step, in which we state our conclusion in context. Typically, I will restate the question verbatim. Dun, 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 dun. We made it to the end. Here's your math humor today, and you're ready to do some practice. I believe the practice only has a few questions, and yeah, we'll do some more tomorrow.